go. Uh, okay, good. Yeah, first of all, thank you for Dr. Yu coming over online to present the distinguished lecture for us. And today's topic is a really interesting topic. It's about building natural conversational agent. And so let me introduce Dr. Yu a little bit more. So Dr. Yu is a fellow of ACM, IEEE, and ISCA, and his research, including he has a very broad range of technical expertise, and his research spans from speech processing, recognition, multimodal interactive, and agentic systems, as well as natural language processing using deep learning techniques. And especially we would like to congratulate him that he just got a IEEE SPS Klaus Shannon Harry Nyquist Technical Achievement Award. And this is for his pioneering contribution to speech recognition and deep learning. So in addition to his technical contributions, Dr. Yu also served on multiple journal editorial boards, and he has chaired the IEEE Speech and Language Processing Technical Committee from 2001 to 2002. Yeah, so thank you again, and the floor is yours, Dr. Yu. Yeah.
Yeah, thank you, Vicky, for the introduction and the invitation. Okay, so today I will talk about some of my thinking about building natural conversational agents. So I will briefly introduce what the conversational agent is, and then mainly describe two kinds of systems people typically build. One is a cascaded system, another one is end-to-end system, and then provide some summary after that. People have dreamed to have a personal conversational agent for decades. Okay. Uh, we have thought that if we have such a system, then basically it can help us achieve a lot of things. So the desirable attributes of such kind of systems will have several aspects. The first one, the agent needs to be very intelligent. Okay, so it's always available and collaborative and can help us to access information, generate ideas, solve problems, and reach goals. Okay, and it needs to be a advanced dialogue system. Basically, it means the agent should be able to understand the input and can track the context, especially if you have a very long conversational history. The system can also track the whole history and through the history information, understand you and your demand. And it can remember preferences you have or you mentioned in the past, and then generates relevant human-like responses. And the third important feature is the multimodal interaction. Of course, people have tried to use text-based dialogue systems, but it's a more natural, always accessible system would include multimodal interaction, including text, including speech, image, video, and even gestures. But today, my talk will mainly focus on the speech modality. As I mentioned, that people have tried to build such kind of systems for decades. So in the early days, like from 1970 to 2000, majority of those systems are rule-based. Basically, you build a specific system for a specific task, and it's highly domain constrained. And I still remember that in the early days, we, for example, just built one single system flight or air ticket bookings, things like that. And such kind of systems usually based on the finite state transducer or state machine using frame-based dialog managers. And the information basically the system try to extract is predefined. So you have a very rigid slot filling flows. And it's not robust because when the user deviate the dialog from the predefined flows, and the system usually get into a strange behavior. Okay. Since 2000, people have gradually switched the focus to machine learning based techniques. Especially when it's closer to 2020, lots of systems are actually built on the deep learning techniques. So during this period, the system is no longer handmade rules. It's usually learned from large corpus using probabilistic data-driven models. And if I remember correctly, since 2010, people have tried to build lots of systems that can work across multiple domains. It's no longer a single domain system. You can actually freely switch between several domains inside a single dialog system. And lots of information can be shared across those domains as well. But the knowledge sharing is still quite limited. It's still hard-coded by the designer of the system. And so there are quite a lot of commercial systems in that area and in that time frame, like Siri, like Alexa, like Google Assistant, and Cortana. But since 2020, also, the field has gone through a complete paradigm shift. Nowadays, almost all those good performing systems based on the large language models instead of early small model or even early machine learning techniques. So due to the intelligence provided by large language model, the dialog system can be fully open domain. You do not need to restrict the domain, and you can easily switch between different tasks and work well across the long history of the dialogues. It can integrate general purpose reasoning and can solve very complicated tasks. Examples like GPT-4o, Gemini 3, 3.1, and Moshi, and OpenCloud nowadays. In all those areas, actually, the dialog systems, also our conversational systems, could evolve with wearable hardwares like necklace, ring, glasses. Okay, so if we truly want to have a natural conversation agent, what kind of properties we hope for? I list several of those. I think those are very important in the practical area. First one, of course, is the high intelligence. The system needs to be able to proactive and collaborative doing reasoning. Okay, if the system behave not intelligently, then usually the user will not feel useful. The system should also have the ability to agentically complete tasks asked for by the users. And the second important property is latency. In human conversation, the latency is usually below 200 milliseconds. but most of the existing systems have response time larger than 1 second. Once it's exceed like 500, 600 millisecond range, then people actually will feel the dialogue is not smooth, basically. And the third one is natural conversation. Majority of systems nowadays is still half duplex or pseudo full duplex. But full duplex is a very important property of the natural conversation, so that two parties, the system and user, can freely exchange ideas, make commands, things like that quickly. But this usually requires the system to deeply understand the contextual information and even understand the emotion of the user. And the fourth one is a robust performance. It's very important that under various conditions, like noisy condition, for example, in a cocktail party situation, or in a room with high reverberant, or when you have multiple talkers, the system can still perform robustly. And the last one is high accessibility. So the system um, needs to respond to users through multimodality information. But no matter which one the system choose to respond, it should be clear, natural. And it's better if the system can integrate multimodal information so that the receiver, which is the user, can more effectively collaborate with the system. So since my talk is mainly focused on the speech component, the speech modality, so for spoken conversational dialogue system or agent, there's one key concept called turn taking. Basically, turn taking is a process where speakers take turns in an orderly manner during the conversation. The goal of turn taking is to minimize the mutual silence or overlap to improve the communication efficiency. There are several fundamental concepts. One is the turn taking cues, usually carried inside the voice rhythm, the breathing, the gaze, the gesture, and semantic completion. So it's a very complicated cue set. Another one is turn end detection and prediction. So basically, the system needs to detect when to take the turn. And the overlap, there are two kinds of overlaps. One is called the interruption. Basically, it's a barging. It's intentional barging. So the system try, or the user or the system try to say something. Or versus back channels. So the listener just gives some short acknowledgement of the information, things like that. The other party should not, stop speaking. So the desirable interaction capabilities will include like systems should be able to detect user interruptions and stop output when appropriate. Okay, should handle pauses without interrupting prematurely. Okay, so if it's just a partial completion of the query, the system should not stop the user. And then the system should provide back-channel acknowledgements to the user during the conversation to encourage the user to continue the conversation. And then the system should have the interrupt ability to interrupt the user when necessary for critical information. But this needs to be there very rarely and strictly. And the system should quickly respond after user actually finishes the query part. So there are two major turn-taking behaviors. One is called half duplex. It allows communications in two directions, but only one direction at a time. Example is the wiki-talkie, where you need to signal the end of the turn by press a button. Okay. But more natural conversation requires something called full duplex. Full duplex also allows for both direction of the communication, but more importantly, it allows for the simultaneous listening and speaking. So when the system is responding to the user, the system also constantly listen to the user's feedback. And by supporting the full duplex communication, the system will be able to support responsive dynamic term management, basically. Of course, to achieve that, the system needs to have the ability to understand the semantic and contextual information very thoroughly. Okay, next I introduce some of those early systems people built to support this. The simplest architecture to achieve conversational, natural conversational agent is through a three-stage system. That's the simplest system where you okay. So basically, you have the user audio query, and you go through a speech recognition system and generate user query in text. Okay, and then you pass that text to a large language model agent, and then the large language model generates the system text response. During this process, the large language model may also search for information, to do reasoning, or call other tools, or arrange other tasks. Okay, but once it generates the text response, it sends the information to a separate TTS system, text-to-speech, to convert it into an audio response. That's the simplest approach. But this is simple and it's modular and it's easy to build. And you can use the best component of each stage. Okay. It's also easy to debug. You can isolate all those problems in each stage. But it has three major problems. The first one is the latency. The total latency of the system from the user audio query to the system audio response is the sum of all the latencies of each component. So it's really hard to make it fast, efficient. If you just blindly build such a kind of system, usually the latency will be larger than 1.5 second, basically. And the second problem is the information loss. When the ASR component converts the audio signal into the text, it already loses a lot of information, especially paralinguistic information. So all those later stage will not be able to access that information, and so the response may not be as good. Okay. And the third one is the error propagation. For example, if you make an error in the ASR component, if the error is critical, for example, the name is wrong, then this error will be propagated into the later stage and cannot be recovered. To solve these problems, people have tried different modifications of the architecture to reduce the latency. For example, the easiest way is to use streaming ASR and streaming TTS. Okay, so basically you process the audio in small chunks. Okay, once you have the partial output, you pass that output into the large language model. Similar for the large language model generate text response. when a system generates some piece of the information, it can pass that into the streaming TTS. The streaming TTS can start generating the audio signal. By using streaming ASR and the streaming TTS, the total latency can be reduced to less than 1 second if you carefully engineer your system. But it is usually still very hard to make it sub 500 millisecond. To solve the information loss problem, people, instead of just using the ASR components, they also use something called paralinguistic classifiers. So by passing the user audio query and extract paralinguistic information and pull that as part of the text output, you can basically send that information to the large language model and have that information used by the large language model. And when the large language model generates the response in text, it can also generate the paralinguistic information. For example, the large language model can generate something called happily say something, and then pass that information to the TTS, and the TTS can use that information to guide the process of the generation of the audio signal. So this can partially solve the information loss problem, especially the paralinguistic information. Okay, but just having the stream ASR and stream TTS, you still have the problem because you don't know at which time frame the large language model should start generate the answer instead of waiting for the stream ASR to provide additional input. Okay, so basically you need to have something called VAD to make the decision. The simplest way is to use something called acoustic VAD. So when the system detects that the user is saying something, that the system should start listening, so that the audio will be fed into the stream ASR, so the ASR start to generate text information to the large language model. And when the system detects that the user has already finished speaking by waiting for a period of silence, then the system start to tell the large language model to start generate response, then generate response. Okay, so that's the simplest approach. But because it only depends on the acoustic information, it's usually very difficult to handle the back channels and hesitations, things like that. And so it will cause frequent interruption and delays. And also on the noisy condition, acoustic VAD is not reliable. So people try to enhance that by using something called personalized VAD and semantic VAD. Okay, so the personalized VAD basically means the VAD information is not just based on the audio signal itself, it's also based on who the speaker is. For example, if you use phone as your major agent, then basically the phone can detect who is the owner of the phone, and then use that information to make the decision whether the owner is speaking to the system or not. So the background noise, background side talk can be filtered out. Semantic VAD is important because you need to make the decision not based on the acoustic information alone, but also based on whether the user actually finished the or completed the question. Okay, so usually this requires to make sure the semantic information is completed. So then it will be much more complicated than the previous approach. So here the system needs to detect whether the talker actually started talking, and then when it detects speech, it pass the information to the stream ASR, and the ASR start to send information, the text query, to the semantic VAD, and together with the audio signal, the semantic VAD can jointly make the decision whether it should start listening, continue listening, or start to speak. Okay, so by using this complicated semantic VAD, the system will behave more intelligently. Okay. So that's the three-stage system, which is available quite widely in the early days. But recently, lots of commercial systems are based on something called the two-stage cascaded system. Sometimes they call it thinker-talker system. So now you no longer have a dedicated ASR component. What you have is integrated the ASR and the AM component here. So the user query in audio comes through an audio encoder. The output of the audio encoder is some kind of audio representation. It can be discrete, like a codec, or continuous. Okay. Sometimes they call it codec free. So it can be continuous or discrete. And then when you pass that information to the large language model, the large language model can just use that information as input and then generate the output in text. Okay, so here, square means text, and circle means audio representation. Okay, but the TTS component is still separated as before. Okay, by combining the first two stages into one, the latency can be further reduced. Okay, usually it's easy to make it less than 1 second. And also now this audio representation contains all the information in the audio signal. Basically, the large language model can exploit the whole information stored inside this audio representation, including paralinguistic information. So supposedly this system should have a better overall intelligence than the original one. But the latency is usually still high. By careful engineering, usually you can make it within 0.8 to 1 second, but it's still worse than 500 milliseconds you would like. And information loss still happens in the output side, okay, if you don't do anything special. So people have made some improvement into such kind of systems. So one, of course, is using continuous representation instead of the discrete representation. People have figured out that continuous representation is always better than the discrete one in this case, because two reasons. One is continuous representation does not require the expansion of the token set. Second is continuous representation will not lose information caused by quantization in the discrete representation. Okay, so people have converged to use continuous representation here. The second one is, as I mentioned in the previous slide, in the three-stage system, you can also include the control text. Okay, so for example, happily, sadly, slow in the system representation, and so this can be fed into the streaming TTS to control the generation process to make it more natural. In this system, of course, you also need to have the VAD component to control the flow. Okay, so so the simplest approach is also using the acoustic VAD, especially since you no longer have the ASR, but you have the audio encoder. you need to decide when to fed the audio encoder's output to the large language model, and when to help the large language model start generating response. A more complicated but more effective VD is, of course, as I just mentioned in the previous slide, is to use a personalized VD and the semantic. So in the three-stage system, the semantic VD is usually implemented using a smaller large language model. It's very small, but it can make a simple decision whether the system should start listening or continue listening or stop listening and things like that. But here, you no longer need a separate small large language model to do that. You can put everything into the system. And to do that, basically you need to put the duplex control tokens inside your output and input. You can put that information here, and then when the system generates the output, it also generates whether the system should start to generate new respond, or the system should just stop and wait for the user again, and things like that. You can put all those into the control tokens and generate together with the rest of the response. Okay. Another important thing is to further reduce the perceived latency is to hide the reasoning or information seeking process. Okay. Right now there are three popular approaches for that. One is called speak while thinking. Okay. Because when the large language model, for example, here you have this large language model, when the large language model tries to generate the reasoning process, which is usually a long chain of the COT, so it will take time before it generates a final response to the user. So this process is usually lengthy, and sometimes it needs to access internet to search for additional information or call other tools. So this the time is actually not predictable sometimes. But you can use a small model to generate some minimal committal discourse connectives, like let me think about that, things like that. When the small system generates this response and send to the stream TTS, the larger model can do the complex stuff in the background. And when it's done, then it will start to send out the final answer to the stream TTS, so the user can hear the final answer. So this can hide the reasoning latency. Another approach is called think, verbalize, then speak. The difference is that it still uses another model, but the difference is that in this case, the large language model's reasoning process, which is a stream of the text tokens in the COT, can be fed into another model, and then the model can translate this reasoning process into some text response and then fed into the TTS. Okay, so basically the system will say, oh, now I'm checking something to see whether this is the case, things like that. So basically explain the reasoning process. This can also hide the latency. The user will know that the system is doing something for the user. And third one is the streaming thinker. Okay. The system can quickly, although the system needs to do reasoning, the time can be lengthy, but system can quickly generate some output during this process based on the partial reasoning. Okay, this can reduce the early stage token waiting time. This can also reduce the perceived latency. So these are three typical approaches, but there are many other similar approaches that can be used to reduce the perceived latency. Okay. Um, uh, but of course, people think that the TTS component should also be integrated into the whole system. So people have been trying to develop so-called end-to-end system in the past 2 years. So now there are several differences. First is that now both the input and the output of the large language model are audio representations. Initially, in the two-stage system, the output of the large language model is the text output. Now, the output of the large language model will also be audio representations. Second one is the information passed from the large language model to the TTS is audio token. So basically, you no longer have a traditional TTS. So you only need the streaming vocoder. You convert from the audio representation into the waveform. You no longer have the conventional TTS. And in this vocoder, you can still add additional information like timbre and genre to the vocoder so that the performance can be very natural and follows the designated timbre as you would like. So by doing all those, you basically can further reduce the latency. So the benefit of end-to-end system is that now it's considered to be a holistic modeling. All the complex correlations between input acoustics, the dialogue context, and output acoustics can be learned. And this can avoid the error propagation problem and the information loss problem in the cascaded systems. And then overall optimization can be done end-to-end in a holistic way as well. And now with this, basically you integrate text, audio, if you have video information, you have the video into one single multimodal system. Okay, basically it can integrate perception, reasoning, generation into a single unified neural network and support various cross-modality tasks. And of course, it can reduce the latency. In some implementations, if you have a very simple vocoder, it can be as low as 200 to 300 milliseconds. So it's really similar to the human conversation. But it's expensive, okay? The model needs to be large, okay? And data used to train the model needs to be large as well. Otherwise, the performance is not good enough. In the end-to-end system, we need to make several decisions. The first one is whether you use continuous representation or discrete representation. You have input and output, okay? In the very early days, people just use discrete input representation and discrete output representation. It's called discrete. That's simplest because it can be easily integrated into the large language model. Everything else will be the same. You don't need to modify the large language model architecture, things like that. The only thing you need to do is to expand the token dictionary. Okay. But quantization will lose information, and so the overall intelligence will be degraded. And so later, most of the systems choose the so-called continuous discrete approach. So the input is continuous representation, just like in the thinker-talker architecture. But the output is still discrete, okay, so that it can be easily integrated into the large language model's next token prediction paradigm. You don't need to make a lot of modifications. You just expand the output token set and then use the existing training mechanism to train the model. But as I mentioned, that distributed representation will always lose some information. So most recently, the industry has been um, changing toward continuous input and continuous output architecture to achieve the best quality and low latency. But training the input is easy. You change this from discrete to continuous is easy. But changing the output to be continuous representation basically means now you have two kinds of outputs. One is discrete text token, one is continuous audio token. So you need to have some better approach to train the model. The second question is whether you should use semantic representation or acoustic representation, especially at the output. Okay. So semantic representation only keeps the key semantic information. For example, uh, the meaning of the audio input or the paralinguistic information of the input, things like that. So so it's highly compressive and optimized to capture the key content information. And the semantic representation usually extracted from the self-supervised models like BestIQ, the Hubert, Wave2Vec, WaveAM, things like that. Or you can distill it from supervised models like Whisper or TTA. People have figured out that even though those models typically called semantic, actually the representation extracted from these models contains both semantic and acoustic information. So it's actually mixed representation. Another one is called acoustic representation, which is optimized to um, uh, high fidelity audio reconstruction. So it's especially used for TTS, the vocoder components. Okay, basically it can be sure that if you generate this representation sequence, the vocoder can convert it into a better audio, high fidelity audio response. So because this is optimized for audio reconstruction, it's usually generated based on neural audio codecs like encodec or soundstream, things like that. Acoustic representation has two problems. One is it's very noise sensitive. So when the noise condition changes, the produced acoustic representation changes significantly. And also because it's acoustic, it's not semantic information, so it's much more difficult to be predicted by the large language model because the large language model is mainly focused on the semantic information learned from the large corpus of text. So now people start to switch from the simple semantic or acoustic approach, or they call it single stream approach, to dual stream approach. So basically you have large language model to predict semantic information and then use other approaches to predict acoustic information. You have two processes. So basically means you can predict semantic information and then use another model to reconstruct the acoustic representation and then convert that into the audio. So another issue is now you have two modalities. One is the audio, one is the text. How do you align these two modalities? Okay, there are three popular approaches for that. The first one is basically called the supervised learning. You have the audio input, and you convert that into a representation using audio encoder. Okay, and then you have a classifier. It's a very simple, usually linear classifier um, to do classification tasks. Okay, so you have the, for example, this is widely used for things like ASR. If you want to extract the semantic information, this classifies ASR component, so that you make sure that this audio representation contains the text representation of the audio signal. Or it can be like gender classifiers, emotion classifier, and things like that, so that it can provide you to make sure the uh, audio representation contains the paralinguistic information. So by doing this supervised learning, you can extract the representation to match the semantic you ask for. The second one is called contrastive learning. Basically, you have the audio input, and you have a way to generate the audio semantics. Okay, so this audio semantics can be the uh, uh, ASR result, the text representation of the audio, or the text description of the audio, like whether it's fast speech, whether it's angry speech, something like that, the text description. And then you train a shared audio encoder to convert the audio input to the representation. You have the same audio input, which considered as the positive sample, and you have another which is considered as a negative sample. And the training make sure if it's a positive pair, the semantic representation and the audio encoder generated audio representation um, has high similarity. If it's negative sample, then they have low similarity score. The third one, I think is more interesting, is called consistency learning. The difference is here is that you don't care about the simple the scores, matching scores. Okay? You care about the effect of the representation in the large language model. So this is how it works. So you have the audio input, and you can generate you can using the audio semantic tool like ASR or paralinguistic classifier or some other approach. You can generate the text information, the text representation of the audio input, the text representation of the semantic information. And then you pass that information to a large language model, and the large language model can generate text output. Okay. And then if you have the same audio input, go through your audio encoder to generate audio representation, which is in circles, audio representation. You would hope that this audio representation with the same large language model will generate the same text output. Okay, so basically means if you input the text representation of the audio and audio representation of the audio, the large language model should generate the same result. Okay, by doing this, you can make sure that the audio representation's effect will be the same as the text representation of this audio, given this same large language model. Okay. And this turns to be very important because it can significantly reduce the data needed to train the audio encoder, and to make sure the spoken dialogue system performs equally well and generalizable as the text component. To further make it work, actually, we have generated something called self-generated instruction-free training. It involves several stages. So you have a base large language model, which is text large language model, text LLM. Um, in the first stage, you only care about the semantic information. So you use the approach I just mentioned. You can generate the answer based on the text information. Um, and then in the stage one, you have a or audio encoder, and then you only train the projector. Okay, only train the projector to generate aligned audio representation here. The aligned audio representation is so the projector is trained to make sure the response generated by the base large language model with the input from this TTA projector is the same as that from the text response. So they will be the same. And just like what I just mentioned, that consistent training. Okay, so after this stage, you can have the semantic representation of both modalities aligned. And then in the second stage, you add additional information like meta information or the paralinguistic information. So you have two components. One is a transcript, which is the semantic information transcript, and then another one is the paralinguistic or other meta information here. You pass that through the large language model, it will also generate output. And then here you use the same thing. Okay, you already trained this TTA projector in the stage one, so you make it fixed. And now you have the voice encoder, which is mainly used for to extract paralinguistic information. Now you also have a voice projector here. You only need to train this voice projector and go through this base large language model and make sure when you have this whole the semantic information and then voice projector as the input, the generated text by the large language model is the same as what you would get if you pass the text description of the audio, including the transcript and the paralinguistic information by the large language model. That way, basically, you can align the audio and the text very accurately, and also without using large amount of the training data, you can achieve reliable dialogue response. Another thing people have tried to work is the usage of the text intelligence. Okay, the one I mentioned, if you, for example, if you fix the text large language model, you only train the projector, things like that. Basically, you can make sure the text component is still reliable. But even if you do that, without using the approach I just mentioned, when your input is audio signal, the large language model may generate a poor response. Okay, so to handle this problem, people try to use something called chain of modality. This is a very early approach. Basically, you have the audio question, audio input, and then you first generate the text transcript of this audio question. So it's audio question becomes text question, and then text question comes as part of the input, and then large language model generates a text response based on the text question, and then based on the text response generates audio response. Okay, so it's still end to end. You have the input, audio input, and you have the audio response, but you need to go through something similar to chain of thought. You have all those internal process. So basically, it combines everything into one single model, but you still need to do the cascaded processing of each step. So the latency is high. Okay. So to solve this problem, people try to use a different approach, which is called interleaving of modality. So instead of generate two differences, one is instead of generating this text question, you remove that. You generate from audio um, queue directly to the text response and the audio response. And so the text response and the audio response are no longer organized in this way. So which means you generate the text response, the whole text response first, and then generate the whole response in audio. But here you generate one text token and then several audio tokens, and then one text token, several audio tokens. By doing this, it's called interleaving of modality. By doing this, basically you can reduce the latency because you don't need to wait until the last text token to start generating the audio response. So the user perceived latency is just here. So it's much higher, much better. And also because you reduced this text queue generation step, it can also significantly reduce the latency. Another approach is parallel generation of modality. So basically, you have the audio question. You don't have any. So this grayed out stuff means you don't have any text question. But you can organize your data in this way. You have the audio question, you have audio response, and you have the text response. Okay, so you do the parallel generation. So each time you have this paired text and audio input token and the paired text and audio output token. Okay, so each time you generate the pair. Okay? By doing this, you can also take advantage of text stuff. To even better handle this, you can also move this token to align with the audio response. But usually this requires a precise alignment between text and audio, so it's not that easy. So people have figured out that the first approach usually is good enough. But if you can shift the audio generation by one token, for example, so that you can always make sure you generate the text token first and then generate the audio. It can will introduce a little bit latency, but it can better use the text information, so it can make the overall performance better. But if you want to make sure the acoustic token is complicated, like RVQ kind of token, then you can do the same thing. But now you generate multiple code books at each step instead of just one. Okay, each one represent one level of the RVQ. Okay, the last one is the streaming, the full duplex streaming process. There are two kinds of basic approaches. One is called channel division, or it's called multi-streaming. Okay, so both input and output have two streams. One is the user stream, one is a system stream. Okay, so in a typical conversational system, you have, for example, here is a user audio, and then system respond with this, and then user say something here, and then system respond with this. Okay, system stream. So the easy way is to just pack it so that it becomes two streams. So if there's nothing, then basically you pack it with zeros here. And so, for example, here is zero. So you convert that into a two-stream representation, and the generation is also two-stream, similar to what I just mentioned. So the prediction will be next token pair prediction. Okay. Because you have two streams, both system and the user can bargain. But another approach is called time division. Basically, it's called interleaving streaming. So you can convert these two streams into a different representation, which is interleaved user system, user system, user system, user system. So you interleave those and convert that or serialize that into one stream. And by doing that, you can also simulate the full duplex behavior. You can further reduce the length because length usually means if it's too long, the performance will degrade. So you can also reduce the length by adding some control signals inside the stream. For example, here you can just, because all those are zeros, you just shrink it into the conventional approach, and you add some special token to indicate that now you have the response from the system, and then you have the mixed response from system and user, things like that. And you can use these control signals to shrink the representation and just learn this CL packet. Okay, so I just briefly mentioned some typical approach to achieve the multimodal conversation agent. Um, uh, as I mentioned that such kind of system is actually complicated to implement. Okay, it requires to have a very strong base large language model combined with a long-term memory, a logical consistency, agentic ability, things like that. And then you need to manage dialogue turns to make the truly full duplex. Actually, yesterday, ByteDance just released their full duplex dialogue system called Speed Duplex, and it behaves quite good actually. So I mentioned that we want the system to be high intelligent, low latency, have natural conversation ability. It can be robust under various conditions and have high accessibility. And now almost all those systems are based on the large language model. It gradually switched from cascaded systems to end-to-end systems, from half duplex system to full duplex systems. Okay. Um, but there are still things needs to be solved. Okay. The first one is the efficiency of the training. Um, so the current situation is that training full duplex end-to-end models requires large, expensive data sets and heavy compute. Is there a way we can actually use existing half duplex or text-only data more effectively to support full duplex conversation without sacrificing large language models' textual intelligence? Another problem is robustness. When you have the background noise, you have multiple speakers, you have strong reverberation, or you have hardware variability, the performance still degrade. Um, so whether there's a way to truly improve the overall turn-taking management under various conditions. Third one is multi-party. So right now, majority of the systems only support two-party, the system and the user. Some experimental systems already support a little limited ability of the multi-party conversation. The multi-party conversation must be able to track the speakers and track the conversation threads and can handle overlaps and addressing and group intentions like that. So it's a much more complicated dialogue system. And then the fourth one is deep integration of multimodality. So what I mentioned here is just solely focused on the speech modality. But of course, when the robot becomes popular, visual cues becomes important, like face, gaze, expression, gestures. It can provide much richer content information and should be utilized. And so we basically need to develop a better approach to fuse all those diverse information. And of course, the last one is better support of the continuous output. Actually, people have tried models like data, and so that the output, input, both input and output are continuous representation. But this training process is actually very tricky. We've tried that as well. It's very tricky, and the error will accumulate after a while. So how to solve these problems to make it robust, generalizable? It's something we still need to explore. Okay, these are some of the um, papers. Now, if you have time, if you have a question, we can ask here.
Wow, thank you so much. um, yeah, so is there any question from the audience? If not, maybe I'll start with one. Yeah, there's so much information over here. Um, and I think most of the, oh, let me see. Yeah, I think there's one question from John. Um, so John was asking, can you speak about diarization in multi-party discussions?
Okay, yeah. Let me change this first. So, okay, I don't know what's wrong here. So okay, basically, so diarization is very important. As I mentioned here, basically, um, in the multi-party dialogue system, you do need to know which part is spoken by which person at what time. And so diarization is very important. Um, uh, uh, it's a very active research area as well. Um, but people haven't truly integrated that into the dialogue system. So majority of the diarization work has been focused on like meeting transcription kind of situation. So the system is just a observer. Okay, the system just observes the conversation between humans and try to identify which one belongs to which. Okay. Um, Technique wise, um, people started from like a conventional approach, going also it's also a multi-stage approach, gradually toward end-to-end approach as well. Okay, so in the past you need to identify the single toggle component segments first, and then do feature extraction, and then do clustering, and then do assignment. Um, but now many work has been trying to combine all those together into a end-to-end system, so that when you provide the whole sequence of the audio signal, the system tries to directly generate the timestamp, the speaker, and the transcript in one shot. Of course, this is still not that reliable at this moment. So many systems actually combines both approaches. They use conventional approach as a base information extractor to provide some prior for the end-to-end system. Yeah, but when you combine or use that into the multi-party conversational agent system, then the system needs to do more than just knowing which part is spoken by which. The system also needs to understand the intention of each speaker, whether those conversations are related, and whether the user is addressing to the system or addressing to the other people, and various things like that. So it's much more complicated.
Yeah, great, thank you. So, um, for training end-to-end models, it requires a lot of large data sets. And would you do you have any advice in terms of how to use the data sets efficiently when you don't have a large data set to start with? Yeah.
Yeah. Uh, uh, what's, yeah. Okay. So basically, this architecture is one of the attempts we have made. Um, so give you a simple example. If you want to train a spoken dialogue system, typically you will need to have pairs of the audio input, audio question, and audio output, the audio answer, right? For multi um, uh, stage dialogue, long-term dialogue, you need to have a sequence of those kind of input out stuff, all in audio. So this data is actually quite difficult to get. It's much more sparse than the text training data you can access from the internet. Um, so, for example, if you want to train spoken dialogue system for a specific domain, you can collect data for that domain. But then if you train the model this way, then when you switch the domain, the performance will be very poor. Okay. Um, which means if you want to make sure for all the domains it works well, you need to collect data for all the domains. Okay. But of course, it's impossible for you to predict all the domains. And also, even if you can, because each domain requires a large amount of data, it's very costly to achieve that. So the approach we propose here basically means if the system, that, for example, the text large language model in this case, already have the general purpose ability. So you know that text large language model is trained with tons of data. So basically, it can work in various domains, and it works very well. And so, uh, if we can align the audio and the text directly, so that the expected output is the same, then what we learned is just a mapping from the audio to the semantic. Okay. So whatever you whatever task you want to achieve in the later stages will be handled by the text large language model itself. So you can use a very small amount of data. In our case, we just use ASR data set, okay, a subset of the ASR data set to do the alignment, and the performance is quite good.
Oh, this is very insightful. So for example, if you are working on a domain-specific applications, um, in this case, is it easier to like adapt your large language model to that specific domain in text, and then you can bring in your audio in a later stage?
Uh, you mean you adapt the large language model to the specific domain? Is that what you mean?
Right,
Oh,
right.
yeah, yeah, yeah. If you already have a task-dependent large language model for that task, um, and if the only thing you want to do is to add a speech modality into the system, then you can use a similar approach as well.
Yeah, this is
And
wonderful.
actually, what you get is more general. Yeah. So even if you switch the domain, the audio text alignment can still help you to generalize to other tasks.
This is cool. Thank you. Yeah.
Yeah, I think there are several questions in the text chat about. me see.
Oh, yeah, that's right. I didn't see it.
What do you think about architecture solely handle the task? Turn-taking prediction, voice active projection, if you are aware of. Others have turn-taking ability, trying to integrate it. Okay. Yeah. So, um, uh, there is something called speculative decoding. This has been also used. This is widely used in large language model decoding, but it's also used in the audio or speech large language models. Um, you can consider that as something very similar to the turn-taking prediction. Um, so in some of the architectures, you do want to, so for example, I mentioned all those uh, cascade systems, they actually do require something called semantic VAD. The semantic VAD basically can be considered as a turn-taking predictor. Basically, the whole task it handles is to predict whether this is the right time to start speaking or to start to listen. So that's the only thing it does. So basically, it's a turn-taking predictor, and it's very useful if you have cascaded systems. But if you have the whole true end-to-end systems, then this turn-taking prediction component is actually part of the end-to-end mechanism. So the large language model is supposed to be able to um, learn this pattern directly from um, uh, the representation I just mentioned. Either it's two-stream representation or serialized representation with all those control tokens. So it's supposed to be able to learn that automatically. And then if you have the speculative decoding, it can make some predictions whether the speaker is likely to continue speaking or it will likely to finish. And you can use that to make quicker turnaround as well. Basically, you can reduce the latencies a little bit. And the next question, in noisy multi-speaker environment, do you think about this primary modeling problem system co-design? Oh, okay. Yeah, of course, of course. All those speech systems or spoken dialogue systems um, requires co-design of various components. For example, in the cascade, not doesn't matter whether it's cascade system or end-to-end system I mentioned, you always need AEC component. Okay, if you don't have the AEC component, then it's very likely you will get poor recognition result. So you do need to co-design with the hardware, especially if your hardware is poorly designed. For example, the microphone and speaker are very close to each other. Then it's really hard for the software, the model, to you know to reduce the problem caused by the hardware design. So it's very important you design everything carefully to make the whole system work together. Any other question? One more? Oh, okay.
Is any additional question from the audience? Oh, there's one thing. No. If not, I have another question. So are most of the LLM model here, like transformer-based model, um, I was wondering, are there any state-based based LLM which would or I mean would help in this kind of scenario?
Of course, actually, many frontier labs nowadays they try to use so-called hybrid system. Uh, it's a combination of the conventional or full attention layers together with so-called member layers. Okay, um, so so by combining these two, you can make the reasoning process more efficient, and especially when the history is long. Um, but people do observe that under some conditions, performance may be degraded compared to full transformer model. Um, but I think uh, for signals like audio signals, um, uh, Mamba kind of mechanism may be more suitable, can be more useful in this scenario. So yeah, so people have tried to use kind of this kind of things um, for speech processing as well. I think including the diarization, people have tried to use that kind of models.
Yeah, thank you. Um, let me check. Chat. Yeah, if not, additional questions from the audience, let's thank you, Dr. Yu again for giving us the wonderful talk over here. And thank you for your time.
Yeah, thank you very much
Yeah.
for attending my talk.
Thank
Thank
you.
you.
So we actually recorded this talk. So we will distribute it to anybody who register for this meeting. So and I actually have another announcement. So we are going to have another event next Friday. It's an in-person event. It will be the topic is about deep learning application for video codec. So if you are interested, you can register for the event. I will do the event announcement in a few days. Yeah, thank you so much. Yeah.